Hello, dears. After discussing the translational mechanical system or the modeling of a translational system, here we will discuss the modeling of rotational mechanical system. Rotational mechanical system is handled the same way as translational mechanical system, except in rotational mechanical system, we have torque, which replaces the force in translational mechanical system, and also the angular displacement replaces the translational displacement, which in a translational mechanical system. The component of rotational mechanical system also similar to the component of a translational mechanical system, which will be seen after a while. We are going to depend on the same rule for developing the mathematical model of rotational mechanical system, which Newton's law, which saying in general, we can say the summation of torques equal to J into alpha, where J is the inertia. That means the total of torques equal to alpha into the angular acceleration. That's Newton's law. We are going to use this law to develop the model of rotational mechanical system. Some variables in rotational mechanical system need to be known. They are torque, angular velocity or omega, and angular displacement theta. Remember that the input for rotational mechanical system is torque and the output will be angular displacement theta. Inertia is one of the elements used in modeling of mechanical system, which consider as a energy storage element. It's element which is storing energy in the rotational mechanical system. Consider these notes before we start the rotational mechanical system modeling. The concept of degree of freedom is exactly same as translational mechanical system, except here the elements are going to be rotating, not moving in a translational way. And writing the equation, whatever I taught earlier, and the way of writing the equation will be very similar in rotational mechanical system, except I will keep in my mind that the input in rotational mechanical system is torque and the output is the rotational theta. The elements or the basic mechanical elements used to model rotational mechanical system are spring, which having a constant K, and damper, which having a constant D. So in S domain is going to be expressed as D into S, and inertia, which having the constant of J, and in S domain is going to be expressed as J S square. Let us consider this example where he wants us to develop the transfer function theta2 over t in this system. Of course, he's putting here the physical system where we are having two bearing number 1 and bearing number 2 with inertia. So if I look at this system, when I want to model it in using the basic component of rotational mechanical system, the bearing will be replaced by damper or modeled as a damper. Then the inertia is having two parts. Part here, this part, and this part, where they are in between, there will be some kind of torsion there. There will be kind of torsion at the center, at the middle. So the representation of this phenomena is going to be the whole inertia is not going to be taken as a one piece. It's going to be split into two pieces. This is one piece and this is the other. And in between them, the torsion is represented by spring K. Now, the other side here, the other bearing is going to be another damper. That's how we can model this kind of system. Now, if I want to model it as he mentioned, he want to, or he will tell me what is the input and what is the output. The input for this system is T, as you see here. T is the input, the torque. The output will be theta1 and theta2, but he can select either one. In this question, he select theta2, so the output to be considered as a theta2. Notice that the system is 2 degrees of freedom. It's 2 degrees of freedom because the torque applied will result in two rotation, two angles, theta1 and theta2. That's why the system is 2 degrees of freedom. To build the equation, we are going to follow the same technique as before, same style as before. I'm going to consider there is rotation at J1 and rotation at J2. So I will call it the equation of J1 and the equation of J2. Where in the equation of J1, the equation of J1 here, it's going to be expressed in general, the general format as bracket theta1. Notice it's the same way as before. Minus another bracket theta2 equal to the total torques applied. Second equation will be applied as minus bracket theta1 plus bracket theta2 equal to the total torques. So let us see what to put in each bracket. In the first bracket here, we are going to put the total impedances linked to theta1. Here we are going to put the impedances linking theta1 to theta2. Here we are going to put the total torques. Similarly here, the link between 2 and 1, the impedance linking theta2 to theta1. Then here in this bracket, we are going to put the total impedances connected to theta2 equal to the total torque, but there is no torque applied on the other side. I mean here in this area, in this location, there is no torque. That means the torque is equal to 0. So now if I develop the equation as you have seen earlier, simply we can calculate or solve the equation, the two equations for theta2. When I solve the equations for theta2, we are going to use the Cramer's rule as usual. We will find that since I'm calculating theta2, the coefficient of theta2 to be replaced by t and 0 divided by delta, the coefficient of theta1 and theta2 from both equations will be equal to this value. So finally, I will find that the transfer function theta2 over t equal to k over delta, where delta is shown here. Remember, if this question given to you, you need to find the value of delta. You cannot just put delta. You need to find the value of delta. Here, he just wants you to get clear about the process. So now when I develop the transfer function, the system or the generated system finally, or generated model finally will be input t of s, transfer function, the mathematical expression, and the output will be theta2. Another example where we are going to calculate the transfer function, again theta2 over t for this kind of system. We apply torque here, and the torque is going to cause two thetas, theta1 on inertia 1 and theta2 would be here. But there is discussion here, you need to know it before we proceed. Let us get clear about this point before I start the calculation. Yes. Usually, as I mentioned somewhere before, the rotation or displacement, as I discussed earlier when we were talking about mass, but here I'm talking about rotation. In rotation, when we apply force to this inertia, it's going to rotate. The rotation on the inertia is not going to change. It's going to be the same theta from starting from the beginning till the end. When will I get theta change? After I cross the spring. That means here it's going to be theta. All this location will be the same theta. Once I cross spring and damper, as you see here, we are going to get a new theta. A new theta. Once I cross the spring and damper, here I will get a new theta. Once I cross this damper, I will get a new theta. Okay, let us discuss it again one more time. So here I'm going to say we apply torque, we will get theta1. Theta1 will remain the same until after the spring here, we are going to get theta2 as discussed. Why I am discussing it in this detail? Because notice that theta2 here at this location, there is no inertia. If you want to consider that there is inertia with a value of 0, constant of 0, you can. But even if there is no inertia, you can proceed with the question. So here, there is theta without inertia. There is no rule saying that theta must be with inertia. So inertia is equal to 0 at this location, but still there is theta. Now theta2 will remain here, and after that we are going to get to different theta, but this time it's 0 because of wall. Similarly here it's 0. I hope now it's clear. So we get to the point saying that the system is 2 degrees of freedom because 2 thetas are there. If the system is 2 degrees of freedom, that means it needs 2 equations to describe it. When I want to describe it, I will describe with equation of theta 1. Before I go to the next slide, let me explain it here. And then theta 2. For the equation of theta 1, we are going to write it such that bracket theta 1 minus bracket theta 2 equal to total torque. And when I am at equation 2, we can write it as minus bracket theta 1 plus bracket theta 2 equal to the total torque. Remember, when I am calculating the equation of theta 1, the coefficient of theta 1 is positive here. When I am calculating the coefficient of theta 2, the coefficient of theta 2 is positive. Other than this, the other coefficient will be all negative. Okay, remember another thing here. When I am at theta 1, the other side of the equation, which here, going to be all the torques applied directly to theta 1. So we have only T. When I am at theta 2, when I'm calculating the equation of theta 2, here I'm going to put all the torques applied directly to theta 2. Is there any torque applied here? Nothing. That's why here it's equal to 0. That's what we will see in the next slide. Remember the bracket, I think I discussed it. The bracket here is clear. Here all the impedances connected to theta 1, all the impedances linking theta 2 or theta 1 to theta 2. Here all the torques. Let's come to this one. Here all the impedances, linking theta 1 to theta 2, and here all the impedances at theta 2. So here is the generation of equation, which is exactly same as I discussed earlier. I am putting the system here for us to follow. So notice here all the impedances linked to theta 1, which S square plus S plus 1, S square plus S plus 1, because the constant of inertia is 1, the constant of damper is 1, and the constant of spring is 1. That's why all of them are coming as a 1. So S squared plus S plus 1 into theta 1 of S minus the link between theta 1 here is the link between theta 1 and theta 2. Let me discuss the link here. So if I want to discuss the link, if you remember what I discussed earlier, I said theta 1 will be up to this point. After that, theta 1 will be changed to theta 2 because I reach to spring and damper. And here is the beginning of theta 2. It's going to be up to here, as I discussed earlier. Notice that the link between theta 1 and theta 2, I can call it somehow theta 1 territory and theta 2 territory. Let's say call it like this. The link between them will be these two elements. That's why I put here S plus 1 equal to Ts, because Ts is applied to theta 1. The second equation will be very similar. So we will start by negative the link between theta 2 and theta 1. Remember, I am putting it this way because I want to keep the right order. Here theta 1, here theta 1, here theta 2, here theta 2. That's why I start with the negative. So it's minus the link between theta 1 and theta 2 into theta 1 plus the whole impedances connected to theta 2. Let us check here. We have 2s plus 2. 2s plus 2 because we are having here 1 and here 1. They are connected to theta 2. If you notice here connected, this is connected. And here also we have S, and S. They are connected to theta 2. That's why we found by the end of the day it's 2s plus 2 equal to the total torques. No torques applied there, so it's equal to 0. Now finish. We will solve the equation for theta 2 because he asked us to generate the equation theta 2 over T. So to find the equation for theta 2, we are going to apply Cramer's rule, and it's very clearly shown here, that we have delta, the coefficient of all thetas, and here we replace the second column, because we are calculating theta 2, I'm replacing the coefficient of theta 2 by t and 0. We replace them here, and then we solve the equation. We will find finally that the transfer function, as you see in here, as you can see here, it's not yet finalized. We are still not arranged it nicely. Let's see in the next slide. So here, the rearrangement of the previous equation will be seen here. I'm just rearrange it such that it's theta 2 over t. So when we rearrange it, we are going to get it this way. You can express it like this and it's going to be fine, or you can also make it such that this equation is third order, which can be written as S1 plus 1 into this equation. So if you make it this way, this part will cancel this part, the remaining will be this. So finally the equation will be written this way. Or also you can write it as it's equal to 1 over 2 over s square plus s plus 1 over 2. It can be written like this. Okay, but if you reach to this stage, you are safe. Remember the coefficient of the highest order to be removed always. This is very important. You will find later why we need to do this. But for the modeling by itself, it doesn't matter if you keep it. In the modeling, no problem, keep it. But when we solve for the transient later, you will find that the coefficient is supposed to be unity. Now we will discuss the rotational mechanical system with gear. If there is a gear connected to the rotational mechanical system. Remember that the gear is made or used to change the speed and the torque. So sometimes if we have certain inertia applied, certain torque applied, it's going to cause certain rotation. If I want to decrease the rotation and increase the torque, I need to use gear. Or if I want to increase the speed and reduce the torque, also I can use the gear. If the gear is available in the rotational mechanical system, how am I going to deal with it? That's what will be seen in the next slide. In the theory of gear, we are going to think of it as T1 at one side with theta 1, T1 with theta 1 at one side of the gear. In the other side of the gear is going to be theta 2 and T2. The radius of this gear R1 and the radius of this gear is R2. If the case is like that, like discussed earlier, R1 theta 1 will be equal to R2 theta 2. If we write the equation, we will find that R1 over R2 equal to N1 over N2, because N is proportional to R, of course. N is the number of gears, the number of teeth there. So it's proportional to R. So R1 over R2 equal to N1 over N2, which equal to theta 2 over theta 1. Now, if I will consider the torque here, we will find that the torque T1 into theta 1 equal to T2 into theta 2. We can rewrite the equation to be like this, and this is what I want. T1 over T2 equal to N1 over N2 equal to theta 2 over theta 1. Which means, if I want to travel from theta 1 to theta 2, we will multiply theta 1 into N1 over N2. And if I want to go from T1 to T2, we will multiply T1 into N2 over N1. This is what we want to know. Okay, so I can say here, in terms of a transfer function, T2 equal to T1 into N2 over N1. And theta 2 equal to theta 1 into N1 over N2.